All right, so question number 11, we got some Newton-Raphson method. I'm going to use technology on question number 11 eventually. But for starters, I'm going to do it kind of like it's back in the day we didn't have some technology. So let's also look at this using, say, Bolzano's theorem. So I know y is equal to x squared minus x minus 1. And first thing I need is to figure out where a root might live. So I'm going to plug in something nice and easy. I'm going to say, well, let's maybe let x equal 0. If x is 0, y is negative 1. Cool. So then I know I have a negative value when x is 0. So let me try plugging in something like x is equal to 1. Want to do that, I get 1 minus 1 minus 1. So that's going to give me negative 1 yet again. All right, so this would, if we were being kind of like nerdy, we would know that the axis symmetry would be at 1/2. But this doesn't help me out because I still have two negatives. So let me try a bigger number. Let me try, say, x is equal to 2. So if x is 2, I get 4 minus 2 minus 1. Right, so 4 minus 3 gives us positive 1. And so what we've shown is that when x is equal to, say, 1, and when x is equal to 2, I get a negative and I have a positive. And since we know the quadratics are continuous, there has to be something between 1 and 2 for which our function is equal to 0. All right, so in this case, probably like 1/2 would be a good initial guess. I'm going to just go with, say, x is equal to 1 as my first thought. So when we're using the Newton's-Raphson method, we need our function, which is x squared minus x minus 1. We also need a derivative, which is going to be 2x minus 1. We can set up a kind of a table, this iterative table. We have our initial guess. And so I'm going to make my initial guess, in this case, 1. 1 looks like it's going to be a good one. So then f of x, well, we evaluated the function when x was equal to 1. We got negative 1, so we're not wasting any time, thanks Bolzano's theorem. Second thing we need is the derivative at this initial guess or our value of x, right? So if I plug in 1 into our derivative, 2 times 1 minus 1 is simply 1. Nice, easy slope. And then we need to take some ratios, right? So the ratio of the previous two columns, right? So negative 1 over 1 is equal to 1. And then what do? We take our value, our current x, and we subtract off the previous column, right? So we subtract off that ratio. Right, so when I do that, I would get 1 minus, let's see, 1 minus, this is a negative 1, 1 minus negative 1, which is 2. So I guess I should have started with 2. All right, so then this value here gives us our next guess. So I can plug in 2 and then repeat the process. We've already plugged in 2 into our function, right? That's going to give us positive 1. When I take the derivative at 2, that's going to give us positive 3. This ratio is 1/3. 2 minus 1/3 gives us 5/3, right? So 5/3 would be our next guess. All right, so then that becomes our next guess. We play the plug-in game one more time. If I plugged in 5/3 into our function, I would get 5/3 squared, which is 25 over 9, minus 5/3 minus 1. All right, so this is where things get a little tedious, right? So 5/3 is 15 over 9. 1 is 9 over 9. So this would be 1/9. If we plugged 5/3 into our derivative, 2 times 5/3 minus 1, 10 over 3. So that's going to be 7 over 3. When I take these ratios, 1/9 divided by 7 over 3, that's the same as 1/9 times 3/7. So that is going to be what, 1 over 21 or something like that. That's a really weird way to write 21. I kind of wrote it. So are we doing that right? Let me make sure. So we get 3 over 63. That's 121. So then we'd have 5/3 minus 1 over 21, right? 5 over 3 would be like having 35 over 21. So then our next guess would be 34 over 21 as a fraction. And then we would use 34 over 21 as our next guess. And we do this over and over and over again until we got something pretty close, right? So I'm going to just kind of cheat a little bit here because obviously I'm going to use technology. So 4 iterations, right? So we do one more iteration with this and whatever happens, happens. So if I go to Desmos, hopefully you save this thing. There we go, Newton method. We can put it in our function. We got x squared minus x minus 1. Right, we have our derivative. We can plug in our values, right? So I plugged in 1. That gave me 2 as a guess. I can plug in 2. By plugging in 2 is going to give me 5/3 as a guess, like we saw. Right, so if I plug in 5/3 here, that's going to give me 1.619 as our guess, 1.619, 1.6190476 as our guess. Right, and then we get 618, blah, 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 1.6180344. Right, and then this would be a whole bunch of iterations. You can see, whoa, what the hell? 1.618. Whoa, that's 4. That's not a 1. 1.618, 0344. Right, so we see that we're kind of converging on something like 1.6180344. Right, so that would be kind of our estimate. That would be our guess. Right, so notice that at this point, we're actually better than Desmos. Right, Desmos is a paltry was at 1,000th place. We're already accurate up to, I don't know, much more than that. So this would be our approximation for the root, which is the golden ratio, by the way. That's the goal for this question, to find the golden ratio. Now, we obviously could have done this question using the quadratic formula. I'll just do that down here. Because we have a quadratic, right? We don't need to use fancy methods when we have the quadratic formula. So we have x squared minus x minus 1 is equal to 0. So we get negative b, so negative 1, plus or minus the root of negative 1 squared, 1 minus 4 times a times c, all over 2 times a. All right, so this is going to be 1 plus or minus. We got a radical 5 over 2, which would be our exact solution. And if we did something 1 plus root 5 over 2, we're going to get something really, really close to that. 1 plus the root of 5. This whole thing divided by 2 gives us 1.61803. So you can see how accurate like our guesses were, right? When we looked at our Newton method, we got 1.6180344. Right, so really, really close, right? That's the approximation for the golden ratio. If you don't know what the golden ratio is, like, I don't know, like use Google or something, like embiggen your life. And sound like a Simpson where I don't think it's a real word. So golden ratio, really, really cool thing. I won't like spend time in this video talking about it, but come talk to me in like office hours about golden ratios. That wouldn't be weird or anything. I'm gonna stop talking and end this video.